Okay, so we're now going to look at the graphs of logarithmic functions. So we started the topic looking at the graphs of exponential functions. We did some work with index laws and exponential equations. We've then introduced the logarithm, done some work with logarithms, log laws, solving equations involving logs. And now we want to go and have a look at what does the graph of y equals log of x look like. So what we want to be really clear about is that exponential functions and log functions are inverse functions, okay? Y equals a to the power of x is the inverse of y equals log base a of x, okay? And we've introduced the concept of inverse functions prior to now. And so we're going to use that idea to draw a sketch of what the graph of log base a of x would look like, knowing that it is the inverse function to y equals a to the power of x. So we know that inverse functions are reflections in the line y equals x. So if I draw in, let's try and draw it in straight. I draw in my line y equals x. Actually, I'm going to draw it in as a solid line because I don't want to mislead the fact that it's not an asymptote, okay? Alright, so something like that. It's a bit crooked, sorry. My pen's a bit glitchy, it's sort of jumping. Alright, let's go with that. That's y equals x. So we know that what happens with an inverse function is that all the x and y values swap. So we know that the exponential function y equals a to the power of x has a y-intercept at 0, 1, which means that its inverse function, the log function, will have an x-intercept with coordinates 1, 0. Okay, we know that the point 1a lies on the graph of y equals a to the power of x, and we also therefore know that the point a1 lies on the log graph. We know that negative 1, 1 on a lies on the exponential graph. So we also know that 1 on a, negative 1, lies on the log graph. We know that the exponential graph has an asymptote at y equals 0, and so that means the log graph has an asymptote at x equals 0. Remember, they don't have vertical asymptotes, exponential graphs, so the log graph won't have a horizontal asymptote. So if we join these up, keeping that mirror image of the shape, then this is the graph of y equals log base a of x, the inverse of a to the power of x. So some properties of the log graph. We have an asymptote with equation x equals 0, so a vertical asymptote. We have an x-intercept at 1, 0. We pass through the points, through the points a1 and 1 on a, negative 1. We have a domain that's equal to the range of the exponential, and that is positive real numbers. And we have a range that's equal to the domain of the exponential, which is all the real numbers. Okay, so there's our log shape. So let's be clear about the fact that there is no horizontal asymptote. This graph is not approaching a particular value here. It's continuing to get bigger and bigger and bigger and bigger, albeit at a smaller and smaller rate, kind of like the square root graph does. Okay. It only has the one asymptote, a vertical asymptote. Okay, so we get this sideways exponential graph. If you were to turn your page around anti-clockwise by 90 degrees, you would have a negative exponential, a to the negative x, so an exponential graph. Okay. Alright, so once we, like all our other graph shapes that we've introduced over the course of this term, once we know the basic graph, what does y equals log base a of x look like, we can then apply all our transformations. Now I'm just going to jump across to a different graphing package before we fill this in, just so we can see what happens with the log graph. So over here, at the moment that's quite complicated, the equation, and it's not in a very nice format for you to be able to read, but it is k times log of b times x plus c plus d. So we've got all the transformations happening here. So let's focus first of all just on the k. So at the moment, k is 1, b is 1. and c and d are both 0. So at the moment this is just the graph of log x, okay? And so without any base it's technically log base 10, okay? So it's just the graph of log x. So let's just focus on the k value first, the number out the front of the log, k times log x. So if we make k bigger, we know what that does is dilate the graph from the x-axis. So here k is 2. And you should be able to see that for any x value, the y-coordinate has now doubled. Now, there is a pen functionality in this program, but it's not very nice. So, you know, that height there has now been doubled to that height there. That height there got doubled, so now it goes up here. So the graph has been stretched away from the x-axis by a factor of 2. That height there got doubled down here, okay? As I said, this pen's very inaccurate, apologies. That height there has been doubled down to there. So the graph has been stretched away from the x-axis. Just going to try and remove those annotations. Okay, so k dilates from the x-axis, and that means that the y values get multiplied by the dilation factor. Okay, so it just gets, I guess, less extreme or steeper, depending on which way you want to think about it. Less extreme if I'm thinking about it as an exponential shape. Think about the sort of curvature being quite extreme. It's turning very quickly, whereas when I dilate it, it becomes less extremely curved. Okay, let's put k back to 1. Let's think about b. So now k is 1, so we've got log x. B is 1, so we've got log x. But if we change b, we'll have log of 2x, log of 4x, log of, etc. So that's the dilation from the y-axis when we put the dilation factor inside the function, just multiplying the x value. And we know that when we make the b value bigger, it won't stretch it away from the y-axis, it will squash it in towards the x-axis. Okay? So at the moment, towards the y-axis. So at the moment b is 2, and that's because we've dilated by half from the y-axis. So half from the y-axis, we're halving the x-coordinate. Okay? So dilation by a factor of 1 over b from the y-axis. So obviously if we made b, let's make b, if we were to make b something less than 1, we would see the graph being stretched away from the y-axis. Okay, it sort of looks like it's going down, and it actually can be thought of as a translation down or up, going this way, through some manipulation, but let's stick with what we know so that it's in line with all of our other functions. Now the other thing we didn't talk about with the k, let's have a talk about with b. If I make b a negative value, we know that that would mean log of negative x, so that's going to reflect our graph in the y-axis. Okay, making the x part of the function negative. So our graph ends up around here. Okay, let me put b back to 1, positive 1. And let's just do that same thing with k quickly before we move on to the other two. So k, remember, is dilating from the x-axis. We make k bigger, it stretches away. If we made k something less than 1, it would squash towards the x-axis. So the y-coordinate there is being multiplied by 0.5. So all the y values are half as close to the x-axis. And then if we keep making k smaller, so we get a negative value eventually, we see that our graph has been reflected in the x-axis. So there's when k is negative 1, so that is negative log of x, so that is the log of x graph, which is still there in black, reflected in the x-axis. Okay, let's put k back to 1. Okay, so now let's think about the translations. So c, that's adding or subtracting onto the x, so that's going to move the graph left or right. Okay, so when we move left or right, that's going to also move our asymptote. So remember, when we make c bigger, there'll be x plus a number, and so it's going to go left. So there's x plus 0.2, x plus 0.4, x plus 0.5. So we've gone to the left, here is x plus 2, so the graph has gone to the left by 2 units, and that's going to move the asymptote with it. If I make c a negative number, here we've got x minus 1, and so that has gone to the right by 1. So log of x minus 1 has gone to the right by 1. So that's all those things we already know. And if we translate the graph up and down, so that's going to be our d value, making d bigger moves the graph up, making d smaller moves the graph down. It won't move the asymptote. Okay, so everything we already know about our transformations holds true with the log. So let's go back over here and fill in what we know. So the graph of y equals log a of x is transformed to y equals k times log a of x by dilation by factor k from the x-axis. So that is multiplying all the y coordinates by k. Also, if k is a negative number, we're going to get reflection in the x-axis. So our graph shape is going to go this way instead. Okay. Log base a of nx, now that was called b in the graphics program, so that was our dilation from the y-axis. So log base a of x is transformed to log base a of nx by dilation by factor 1 over n from the y-axis. And if n is negative, so if n is less than 0, we're going to get reflection in the y-axis. And so our graph shape will go this way. Obviously, we could also have both reflections. If we had both reflections, our graph shape is going to go down this way. Okay, so again, the first thing I want you to think about, like we talked about with the exponentials, is which direction is my curve going, and then what are my translations, where are my x and y intercepts. Okay. So log base a of x plus or minus b is it's been transformed to that by translation by b units left or right. Okay, so let's be clear about, for example, if we had y equals log base a of x plus 2, this would mean to the left by 2. If we had y equals log base a of x minus 4, we would be going to the right by 4. And that's obviously going to change the asymptote. If we're adding and subtracting onto the end of the function, it is translation by c units up or down. For example, if we had y equals log a of x plus 3, that's going to be up by 3. If we had y equals log a of x minus 1, that's going to be down by 1. Okay, so think about your direction of the curve based on reflections. Think about your translations, particularly where is your asymptote. Calculate x and y intercepts to draw your graph. Okay, dilations don't really have a massive impact on how you draw the graph, although if you were going to draw 2 times log a of x versus 10 times log a of x, you would need to have that relative scale correct. Okay, let's draw some graphs. Oh, before we draw some graphs, let's also have a think about the fact that they're inverse functions. So example 1 says find the inverse function of f of x equals 3 times log base 2 of x plus 1. So if my original function is a log function with a base of 2, I will expect my inverse function to be an exponential function with a base of 2. Okay, so we've talked about the process here. It's really important that you don't write mathematically incorrect statements here. So I'm going to do 2 things at once by straight away letting x equal f of y, which immediately gives me x equals 3 times log base 2 of y plus 1. And that's we've swapped x and y, we've introduced y into the problem and swapped x and y all at once in that first step. Alternatively, what you would need to write is let y equal f of x, okay? So let y equal the function, which is 3 times log base 2 of x plus 1. And then you need to swap x and y, and you must write swap x and y in between those 2 lines because they're not, there's no algebraic logic to go straight from there to there. So you can't just have this line written immediately below this line with nothing in between, okay? Alright, I'm going to delete that to give me some room. But again, being careful about what you write to make sure that you're not writing mathematically incorrect statements. So now we're going to solve for y. So I'm going to take away 1. I'm going to divide by 3. And then I'm going to convert from a log equation to an exponential equation. Log base 2 of y equals that fraction means that y equals 2 to the power of that fraction. So there is my exponential equation with a base of 2. Find the inverse function, so let's answer that question. Therefore, f to the negative 1 of x is equal to 2 to the power of x minus 1 over 3. Doesn't ask for domain or range, although and there's been no restriction here, so the domain of the inverse is equal to the range of the original. The range of a log function is r. The domain of this exponential function is r. So there's no restriction. So it's not really necessary to state the domain because it is its implied domain. Okay, example 2. Find the inverse function of f of x equals 2 to the power of x plus 1 minus 4. And hence sketch the graph of both y equals f of x and y equals inverse f of x on the same set of axes. Okay, so let's first of all find the inverse function. So let's let x equal f of y, which means I'm going to have, x equals 2 to the power of y plus 1, take away 4. So I'm going to add 4. I'm solving for y now. I'm going to change to a log equation to free the y out of the power. So it's going to be log base 2 of x plus 4 equals y plus 1. And then we can take away 1. So y equals log base 2 of x plus 4 minus 1. So that is my inverse function. So log base 2 of x plus 4 minus 1. Okay, let's focus on sketching that exponential graph. So it's an exponential with a base of 2. It has gone to the left by 2 and down by 4. No reflections. So my asymptote. Now we do want to be, because we're going to draw a function and its inverse on the same axes, we do want to try to keep things a bit square. So I'm going to use the same scale on my x-axis as I do on my y-axis. Sorry, that's a bit crooked. Okay, so y equals negative 4 is the asymptote. I'm going to try and use that similar sort of scale on our x-axis, which will help us to be able to see nice and clearly that reflection in y equals x, because it will mean the line y equals x is actually at a 45-degree angle to the x and y axes. Okay, so Alright, now I think my scale got a bit big there because that should be negative 4 there. Okay, so we're drawing the exponential graph. So we've got the asymptote drawn in at negative 4. We know it's going to be going in this direction, so we want to consider where that y-intercept and that x-intercept will be. Alright, so let's find the y-intercept. Let x equal 0, so it'll be 2 to the power of 1 minus 4. 2 minus 4 is minus 2. So it is going to go through minus 2. My x-intercept is 0 equals 2 to the x plus 1 minus 4. So 4 equals 2 to the x plus 1. 4 is 2 squared. Don't need logs here. So 2 is equal to x plus 1, which means that x equals 1. Okay, so we get our exponential graph, which is our original function. So when you're going to draw two graphs on the same axes, make sure that you label them, which one's which. So I'm going to change my pen color here to draw the other one. So the inverse function, you shouldn't need to be looking at this equation to draw it. Okay, if your original function had an asymptote when y equals negative 4, your inverse function has an asymptote when x equals negative 4. Now, they should intersect on that line y equals x because that's the point negative 4, negative 4. Okay. Now, my original graph, sorry, I didn't label my intercepts here, so this was 0, negative 2, this is 1, 0. So my inverse function goes through goes through negative 2, 0 there. And my inverse function goes through 0, 1, which is there. They should also cross. If I've got the line y equals x drawn in, the graph should actually cross on the line y equals x. So I'm going to try and make sure I hit those points when I draw my graph shape in as well. Oops. Slightly missed that one, but we'll pretend. So there's my inverse function in purple, in that pinky purple colour. Intercepts labelled. It doesn't ask us to label the points of intersection between the two graphs. That's actually not a solvable equation without your CAS. So we're just drawing the two graphs on the same set of axes. Okay. Oh, sorry, missing a page here. There we go. Example 3. So now we just want to sketch some log graphs. So sketch the graph of y equals negative log base 3 of negative x. Okay, so we've got reflection in the x-axis and reflection in the y-axis. So it's going to be our normal log shape goes this way, reflecting it in the x-axis means it goes this way, reflecting that in the y-axis means it's going to go this way. Asymptote won't have moved, so it's still going to be at x equals 0, the y-axis. And we just need to calculate that x-intercept, and we will need an additional point on this graph. Okay, so we're going to have let's calculate the x-intercept. So x-intercept is going to be y equals, 0 equals negative log base 3 of negative x. So that's the same as saying log base 3 of negative x equals 0, so just multiplying both sides by negative 1 or adding the log onto the left hand side. So negative x equals 3 to the power of 0, which means negative x equals 1, so x is negative 1. Okay. Alright, so we're going this way. Now we're going to need another point on that because that could be the graph of negative log base anything of negative x. So we need another point. So I'm going to put when x equals negative 2 perhaps, or negative 3 might be even better. That means we get y equals negative log base 3 of negative 3, so that's 3, and so that's negative 1. Okay, so this is the point negative 3, negative 1. This is the point negative 1, 0. Asymptote is the y-axis, so don't need to label it separately, and there's my graph. Okay, example 4, sketch the graph of 2 times log base 10 of x plus 3. So we've got dilation from the x-axis by a factor of 2. That's not going to change how I draw it, that'll just change where the intercepts are when I calculate them. And we're also going to the left by 3. So left by 3 means our asymptote is going to have equation x equals negative 3. Okay. And a bit like when we talked about domain and range, you can also think about your asymptote from your domain. So we know that the thing inside the log has to be positive, x plus 3 has to be bigger than 0, means x has to be bigger than negative 3. So therefore your asymptote must be at negative 3 and your graph must be over here to the right. Okay, so that can help you as well thinking through the domain. And we're asked to state domain and range, so we'll do that once we've drawn our graph. Okay, so let's think about no reflection, so the shape's still going to go that way. So our y-axis, our x-axis, x equals negative 3. Let's calculate the x-intercept, and there'll be both intercepts actually, because it's going to go like this, so we're going to cross both axes. So let's find both of them. That will be our 2 points. So let y equal 0 for your x-intercept. Divide by 2. So again, don't put that up into the power, that doesn't help you. Just divide by 2, goes away. Converting to an exponential, so it'll be 10 to the power of 0 equals x plus 3. So that's 1 equals x plus 3. And so x is 1 minus 3, so negative 2. So again, make sure that's in the right position relative to where you've got your asymptote. So that should be negative 2 there, negative 1 there, basically. So it should be 2/3 of the way along. Okay. So your y-intercept, you're going to let x equal 0. So you're going to have 2 times log base 10 of 3. Can't do anything with that. If you want to be able to write it a bit more neatly, you could write it as log base 10 of 9. Okay, log base 10 of 10 would be 1, so log base 10 of 9 will be a bit less than 1. Okay, so again, I haven't got any other numbers on my y-axis though, so I'll just draw my graph and then label that point. So that is the point 0 log base 10 of 9, or 2 times log base 10 of 3, and this is the point 0, negative 2. Sorry, negative 2, 0. Asymptote, dashed straight line labelled with equation, 2 points on my log graph, and so we're all done. Okay, state the domain and range was the other part of the question. So we've got, was it called F? No, so I won't call it domain of F because it didn't have a label, we'll just call it domain. So the domain is clearly from negative 3 to infinity. The asymptote tells us about the domain, and the range of any log graph is R. Sketch the graph of log base 2 of 8 minus x and state the domain and range. Okay, so if you've got y equals log base 2 of 8 minus x, you need to be careful about reading off those transformations. That's the same as negative x minus 8. So you've got reflection in the y-axis, that's the negative in there, and then to the right by 8. Okay, so be careful about those, how you read those out. Now, if you have trouble with that, I would advise thinking about the domain first. 8 minus x has to be bigger than 0. We know that log of whatever's inside the log has to be bigger than 0, which means minus x is bigger than minus 8, which means x is less than 8. Okay, so therefore you know your graph has an asymptote at 8, and the graph is less than that, so it's going to be back this way. Okay, so that helps you to think through that reflected in the y-axis and then translated to the right by 8 to get it in the right position. Okay, so we're going to need to think about x and y-intercept. So maybe let's do that. X-intercept, we'll let y equal 0, so 0 equals log base 2 of 8 minus x. So that is 2 to the 0 equals 8 minus x, or 1 equals 8 minus x. Subtracting 8, negative 7 is negative x, so x equals 7 is my x-intercept. And my y-intercept, we'll let x equal 0, will be log base 2 of 8. And that is 2 to the power of what equals 8, so that's actually going to be 3. So you wouldn't leave that as log base 2 of 8, that's not simplified. 8 is 2 cubed, and so therefore that equals 3. Okay, so we've got everything we need. We're going to have my y-axis over here, because my asymptote's quite a long way over here. At x equals 8. Again, let's try and get 7 in about the right spots. That would be 4, that would be 6, so this would be 7. Okay, my y-intercept's going to be at 3. I don't need to be using the same scale, so I'm just going to draw in my shape and then label the point as 3 when I get there. And so that is 0, 3, and this point is 7, 0, and I've got my asymptote labelled with its equation. So we've got 2 points and asymptote with equation. Okay, sketching log graphs with your CAS is exactly the same as sketching any other graph with your CAS, remembering, however, that your CAS does not display asymptotes. So if you think that there is an asymptote at a certain point, what I would suggest when it's a vertical asymptote is to use graph trace. So menu 5.1 to select graph trace. That will then put a cursor on your graph. If you think there is an asymptote when x equals 2, as there is in this example, once you're in trace mode, you simply type the number 2. You don't need to click anywhere. Once you're in trace mode, just press the number 2 on the keypad, and up on the screen it will automatically appear with x equals 2. Press enter and it'll jump to the point where x equals 2, and because x equals 2 is not a point on this graph, it'll do what it's doing here, and it'll mark that point as undefined, and it'll draw that horizontal line, and you'll be able to get a sense of whether you think, yes, in fact that is the asymptote. It's not a precise way of working out the asymptote. You really need to be able to understand about log graphs and where it is so that you can draw it in at the right place. The work today is from a worksheet which I'll be providing to you, or which you can also download from our Canvas page.